This section explains the 3D Gaussian Splatting, 3DGS, model and code implementation. Let's first look at the 3DGS model overview. 3D Gaussian Splatting is a neural point-based rendering method where each 3D point is represented as a Gaussian distribution rather than a simple discrete point. This allows for smooth, differentiable rendering and enables high-quality novel view synthesis. The model represents each point using as follows. Each point is projected into 2D space using a Gaussian function, allowing smooth interpolation and blending in image space. Mathematical formulation of 3D Gaussians. Each 3D Gaussian is parameterized by as follows. Mean, position in 3D space. Covariance matrix, shape and orientation of Gaussian in 3D space. Rotation matrix Ri is the rotation matrix from quaternion. Scale matrix Si is the scale matrix, diagonal matrix with squared scales. Projection from 3D to 2D. To render a 3D Gaussian, it must be projected onto a 2D image plane using a camera model. Perspective projection. Given a camera with intrinsic matrix K and extrinsic transformation, rotation RC and translation TC. A 3D point PI in world space is transformed into camera space as follows. The 2D image coordinates UV are obtained via perspective projection. Projecting the covariance matrix. To obtain the 2D covariance matrix in screen space, we apply the Jacobian of the projection function as follows. Using this Jacobian, the 2D covariance matrix in screen space is as follows. Rendering 2D Gaussian splats. Each projected Gaussian is rendered using a 2D Gaussian function as follows. X is the pixel coordinate. Mu is the projected mean. Sigma is the 2D covariance matrix. Volume rendering. Alpha blending for compositing. To combine multiple Gaussians in an image, we use alpha blending as follows. Alpha is the opacity. C is the color of the Gaussian. This ensures smooth blending of overlapping Gaussians. Now we implement the 3DGS code. Gaussian Splatting 3D class. Testing the 3DGS model.